Welcome to This Explainer. If you've spent any time in a lab, you know physical chemistry is generally full of predictable, rock-solid rules. But today, we're diving into the fascinating moments where those rules get seriously tested. We're talking hidden structures in unknown liquids and chemical math that literally lies to us. Let's get into it.
Here's our roadmap for today. We'll kick things off by solving the unknown, then look at the magic of indicators. After that, we're capturing moving electrons, measuring standard electrode potential, and finally unpacking the oxidation number fallacy.
Part 1. Solving the unknown.
Let's start with a classic lab scenario, figuring out exactly what's hiding inside a mystery liquid. Titration is basically a chemical matchmaking game. We take our titrant, a known, highly calibrated standard, and pit it against the analyte, which is our mystery substance. By watching how they interact, the known completely forces the unknown to reveal its properties.
The physical setup is pretty standard. You've got the known titrant up in the burette and your unknown analyte down in the flask. The entire goal here is absolute precision. You are carefully chasing that exact, singular drop where the acid perfectly neutralizes the base. That magical moment is called the equivalence point.
Now, as you probably know, doing an experiment just once in chemistry is basically as good as not doing it at all. To prove your neutralization wasn't just a fluke from having a heavy hand on the dial, you absolutely have to get 3 concordant readings. It's all about proving your results are theoretically sound through physical repetition.
Part 2. The magic of indicators.
This brings us to a rather obvious hurdle. How on earth do we actually see that exact equivalence point when both liquids might look like clear water? Well, chemistry gives us 2 distinct ways to solve this. Some solutions are total divas, meaning they bring their own color to the party. Manganate, for instance, has a natural dark purple or pink color. It's completely self-indicating. When the reaction finishes, the color just naturally vanishes. But others, like chromate, are totally invisible during the reaction. They actually need external chemical helpers, like diphenylene, to physically trigger a color change so our human eyes can spot the equivalence point.
And honestly, the quirks of these indicators really matter in a real-world lab. If you volunteer to mix phenolphthalein, you better know beforehand that it is insoluble in cold water. You literally have to use warm water to dissolve it. Meanwhile, starch is famous for turning the striking blue or pale yellow the second it reacts with iodine. And you don't even always need synthetic chemicals for this. Everyday natural items like red rose petals or turmeric can actually act as fantastic visual cues.
Part 3. Capturing moving electrons.
Okay, we've solved unknown liquids. But what about energy? We know the redox dynamics when you mix elements like zinc and copper, but if they just share the same beaker, all that amazing microscopic energy is lost as useless heat. The brilliant workaround is isolation. By putting zinc and copper into their own separate half cells, we physically force the electrons to travel a long distance through a wire to get from one to the other. And that forced migration? That is exactly how we harness usable electricity.
There's a catch, though. To prevent charge buildup from just dead stopping the flow, we have to drop in a salt bridge, typically a U-shaped tube filled with potassium chloride or ammonium. Think of it as the ultimate chemical peacekeeper. It magically maintains electrical neutrality without letting the warring liquid factions physically mix, which perfectly completes our Daniell-Cell circuit.
The flow dynamics here present a really fascinating juxtaposition. Physically speaking, the actual electrons are flowing away from the zinc and into the copper. But because electrons carry a negative charge, our conventional electric current is calculated as flowing in the exact opposite direction, from the copper back to the zinc.
Part 4. Standard electrode potential.
With our battery built, we obviously need a standardized metric to measure how forcefully one metal pushes its electrons onto another. We measure this relative tendency against a 0-volt standard at a standard 298 Kelvin. But here is the somewhat counterintuitive part you really need to remember. A negative value actually indicates more reducing power. The deeper into the negatives you go, the stronger the reducing agent is.
Part 5. The oxidation number fallacy.
Now for the absolute plot twist of this explainer. Up until now, we've relied pretty heavily on formulas, but we've reached a point where standard chemical math completely lies to us. Let's look at a classic puzzle, the compound H2SO5. If you crunch the standard oxidation numbers, meaning hydrogen is +1, oxygen is -2, the math boldly claims that sulfur must have an oxidation state of +8 to balance everything to 0. But wait, does an oxidation state of +8 for sulfur even make logical sense in reality?
The answer is a hard no. Since sulfur sits in group 16 of the periodic table, its absolute theoretical maximum is only +6. It literally only has 6 valence electrons to give. It can't give 8. So why on earth did our seemingly flawless math spit out an 8?
Here's the brilliant revelation. The blind mathematical calculation completely fails because it simply assumes all 5 oxygen atoms hold a standard -2 charge. It entirely ignores the structural reality of the molecule itself. You see, H2SO5 hides a structural secret called a peroxide linkage, where the oxidation state of 2 of those oxygen atoms actually drops to -1. The moment you factor in that structural reality, the math corrects itself and brings sulfur perfectly back down to +6.
And this principle applies across the board. Standard calculations work perfectly fine for decoding elements like phosphorus in NH2PO4 or manganese in K2MnO4. But oxygen? It loves to break the mold. In a peroxide, it's -1. In a superoxide, it drops to a truly bizarre -1/2. Once you understand these rules, you realize that the physical structure absolutely dictates the chemical state.
Now, because calculating all of this can get incredibly tricky, chemists actually developed a brilliant shortcut for naming compounds. The Stock method removes all the guesswork by placing the exact oxidation state right there in the name using Roman numerals. So when you see tin IV oxide, that Roman numeral IV instantly tells you tin has a +4 valency. You just cross that +4 of tin with the standard -2 of oxygen, and it effortlessly translates into the beautiful simple formula SNO.
Before we wrap things up, let's look at one extreme behavioral anomaly that ties all of this together, featuring the surprisingly aggressive compound silver difluoride, or AgF2. It is notoriously volatile and reactive. But why?
Well, it comes back to states. Silver naturally prefers to be highly stable in a +1 state, but in AgF2, it's being forcibly pushed into a +2 state. Because silver is absolutely miserable and highly unstable in that plus state, it acts incredibly aggressively to steal an electron from literally anything nearby just to reduce itself back down to +1. That desperate forced theft makes it a phenomenally potent oxidizing agent.
Which brings us to our final thought. Whether we're hunting for unknown solutions or calculating valencies, blind math is never enough. When simple math contradicts the rules of nature, the structural reality of the molecule always holds the true answer. It really makes you wonder, what other established mathematical formulas in science are currently hiding a physical truth we just haven't visualized yet? Thanks for joining me on this explainer.